Okay, so in this video we're going to be covering half-lives for first and second order reactions. All right, hopefully you've heard of the concept of a half-life. All right, so first of all, what is half-life? Half-life is the time that it takes for the concentration of anything to be cut in half, or the amount of anything to be cut in half. All right, so if we have a liter of something, of a reaction mixture, and the reaction is occurring in that volume, concentration would be the same as the amount of it left. So how could we mathematically define this? All right, so the way that we're going to mathematically define what a half-life is to say, so remember, normally we say, concentration of A with a little t here, where T is the concentration at that time. All right. Well, the half-life is going to be the concentration at that. What is the time where the concentration is half of what it originally was? So we can define this right here means the concentration when it is half of its original concentration. So we can define the concentration at its half-life as concentration of A with the little t1/2 as a subscript. All right, and what that's going to be equal to is 1/2 of the original concentration. All right, and so remember, the original concentration we define as the concentration at time equals 0. All right, so that's got the little 0 as the subscript here. All right, so we should be able to use some of the equations that we have used so far. So remember, we have an integrated rate law for a first order reaction, which looks like this. All right, and we have an integrated rate law for a second order reaction that looks like this. And we should be able to just substitute whenever we have AT, we're going to be putting in what we've derived so far. Actually, I'll just go ahead and uncover this. All right, so if this is, and actually we're going to be using the other version of the integrated rate law. Remember that it could have been expressed as either this form right here, all right, or applying the natural log rules, ln, and actually this line should not extend under the ln. It's the ln of this quotient here. All right, we're going to be using that version of it. All right, so substituting in for the concentration at the half-life, we would say, again, this is what the concentration is at that point. So we're going to have 1/2 of that over this. All right, and at that point, you'll see that our initial concentrations would cancel out, so you're just left with ln of 1/2, all right, equals negative k to the times the half-life time, and we can then rearrange, and we end up getting this, which, and the thing is, taking the natural log of 1/2, that's taking the natural log of a number, an actual number, and we can calculate what that number is, and this is what you get. So one thing I want to point out about this is what this indicates is that if you have a first order reaction, all right, the amount of time that it takes for that concentration to get cut in half is going to be the same regardless of whatever the original concentration is. So if you've got a really concentrated reaction, it'll take the same amount of time for that concentration to get cut in half as if you have a dilute reaction. All right, and the reason for that is that this expression does not contain anything having to do with the original concentration. All right, let's contrast that with the second order. Okay, again, the integrated rate law for the second order equation is this right here. And again, we're going to do the same trick where when we're at the half-life, we can say that at that point the concentration is 1/2 of the original concentration. So we substitute that in right here. All right, so moving this to that side, you'll see that we have an equation here where we could factor out, if you think of this as 2 times 1 over top of concentration of A sub 0, 1 over a sub 0 will factor out, so we can factor this out, and we can have 2. So 2 is what we'd have left over here. 1 is what we'd have left over here. 2 minus 1, that's going to give me 1. So on the left side, we have 1 over a sub 0 equals k t. So solving for the half-life, we would get this expression here. All right. So the important thing to remember is that what this indicates is that if you have a second order equation, the amount, your original concentration actually affects what the half-life would be. All right. Remember, for a first order equation, it takes the same amount of time for the concentration to get cut in half, no matter what the original concentration is. All right. But what this indicates is that for a second order equation, if you have a more concentrated original reaction, all right, that means we're going to have a larger number in the denominator. That means the overall half-life is going to be smaller. All right. So the more concentrated it is, the shorter the amount of time it's going to take to get to that concentration where it's half of the original. All right. So hopefully that makes sense.